Okay, well, thank you for inviting me to speak. Yeah, so I guess I spent a lot of time thinking about fundamental groups a long time ago. Not so much recently, but I've sort of come back in a strange direction, at least strange for me. But let me start with maybe an introduction for a more classical setting, which is Kaehler groups, which is the direction I came from. So I won't write it down, but a Kaehler group is a group which is the fundamental group of a compact Kaehler manifold. So for example, a smooth projective variety over C is its fundamental group is a Kaehler group. And so I guess maybe historically the first deep result is Deligne, Griffiths, Morgan, Sullivan, but that's going in a slightly different direction than I want to talk about. So let me start with theorem of Gromov, which is for me very influential. So I think this is around 89, 88. I don't remember the exact date. And it says that a Kaehler group is indecomposable with respect to free products. So let me just, since I'm out of space, let me just write it as star, free product. So that's the co-product in the category of groups. And so the paper of Gromov is quite short. It's a compte-rendu note, maybe 3-4 pages. And so with some people, one of whom is here, I mean, besides myself, we spent some time thinking about it. So we sort of generalized it. So this is a theorem by myself, Bresler, and Ramachandran from early 90s. And it's maybe a little more technical to state. Let me state the full version and then I'll explain it. So if you take a group which is given by an extension of a group with infinitely many ends by a finitely generated group, so G is just going to be a finitely generated group, is an extension of a group. So I'll have to explain what this is, but let me write it first. By a finitely generated group, then it's not Kaehler. So, I mean, before getting into the explanation, let me just give you a quick corollary where you can use it. So it's actually a generalization of this, but where you can use it beyond Gromov is, for example, braid groups are not Kaehler. And the proof, I won't go into the details, but you can basically exhibit braid groups as such an extension. Okay. And so maybe I should say this because most people are not familiar with this concept, but I'll draw some pictures. So you can visualize a group, finitely generated group by its Cayley graph. And let me draw two examples, and I notice there's some colors, so I don't know if this is gratuitous use of colors, but I'll use blue for first example. So this is the Kaehler graph of the integers. And the second example, let's say in green, will be a free group on two letters, however you like to write it. And if you draw it, I won't explain exactly what that means, but hopefully you can understand the picture is going to be an infinite tree. And ends means pretty much what you think it is. This has two ends, and this has infinitely many ends, right? And that's exactly what this concept is. And there's a theorem of Stalin's, which is a very beautiful characterization of this, which I want to quickly remind you of, from late 60s. So this says that, so what's the relationship between this theorem and this theorem? Basically, they look like free products or free products with amalgamation. And so let me state the exact thing. So to avoid any trivial exceptions, so a non-virtually cyclic group meaning it shouldn't contain Z or Z if you prefer as a finite index subgroup. Has infinitely many ends. Let me just be lazy. If and only if it's a free product or an HNN extension with amalgamation where the amalgamating group is finite. Be lazy and not write the whole thing where the amalgamating group is finite. So, for example, a free group, this one here, has infinitely many ends, and in sense, this is saying the converse, that things with infinitely many ends are very close, at least morally, to such a picture. Okay, so that's the group theoretic content of this statement. And now let me just say a few more things. This is still the introduction. A much more recent result, which got me re-interested in Kaehler groups. It's a theorem from 2012. And you can correct me if I have the history wrong, but I think it's independently due to Biswas and Mahan. He tends to use his initials as his last name, but I prefer to use this. And Kachik. Is there a C? Yeah. 2012. Okay, so this is a beautiful theorem. I mean, it was actually an open question for a long time, and I'm happy that it's settled. They classify one-relator Kaehler groups. And there's an obvious example, namely the group of a surface. By surface, I mean curve, a Riemann surface. And there's a few more examples which are very close. So the only one-relator Kaehler groups, one-relator meaning have exactly one relation, let me be lazy and just say K group, are of the following form. So maybe I can squeeze it here so I don't have to rewrite everything. We'll just give it by generators and relations. So I have 2G generators, where G is some fixed integer. And then a relation, a one-relator group, so I should write down a single relation. And this looks familiar, I think, to everyone. And if I just stop here, this would be a surface group. But what you can do in addition to this is to take this to some power. And this is like a orbifold, one orbifold point of order m. And these actually come up in examples using elliptic surfaces. So it's actually an if and only if. And that's all I wanted to say about the sort of motivational part. So now let me start the actual talk. So I've gotten interested recently in positive characteristic, and since I'm coming from the complex side, it's a little bit strange but interesting. So most of the tools coming from Hodge theory just don't work, at least as far as I can tell, but it's amazing that you can do quite a bit. So let me fix some notation. So let me call it section 2. So let's just give a title here, pro-finite case. So over here, everything was a discrete group, and now I'm going to do this case. So I'm going to fix just some notation in advance. So P will be a prime. It could be 0. But I'm mostly interested in the case of positive characteristic. Let's say K, if I need it, is a field of characteristic P, and it'll be algebraically closed. Actually, for the purposes of this talk, you may as well just take the algebraic closure of the prime field. Okay. So, right, and as usual, if I need another prime for whatever reason, historical reasons, it's called L, so this is another prime. This won't come up until later. Another meaning different from P. Okay, so I haven't said anything yet. Let me now get into the actual story. So I'm interested in the Etale fundamental group, but it behaves in a really strange way for me at the prime P. So I'm going to go away from that prime. So if X is a variety, everything will be over K. Let's say normal, actually smooth is fine. And I'm actually interested in the projective case for now. And then let me write pi 1. Now it'll stand for Grothendieck's Etale fundamental group, but I'm going to stay away from, the base point won't matter. And this is the prime to P part. Or I might put that here. So this is I'll have to explain what I mean. Okay. So let me just say a few more words of terminology and notation, so then I can state some theorems. So let's just say a P prime group is a finite group whose order is prime to P. And then a pro P prime group is the inverse limit of such. And then now I can say, if it wasn't already clear what this means, this is the maximal pro P prime free prime quotient of this. Of the Etale fundamental group. So you're throwing away a lot of information, but the information you're throwing away is in some sense very not topological. I mean, even for elliptic curves, the answer is sensitive to the choice. Okay. So keep this theorem in mind, which is still lingering on the blackboard, and I need to generalize it. Maybe not exactly generalize it, but sort of give an analog. So I need to explain the analog of these words. So that'll take a few minutes. Okay, so the first thing, this is all standard. There's a book by Rebus and Zaletsky on pro-finite groups. You can look at a lot of the stuff in there. So first of all, there are coproducts in this category. Which category? The category of p-prime groups. Well, I just mean of two. Yeah, sorry, two pairwise. Probably even arbitrary, but this is all I care about. The pro guys. Groups. And this is just my notation because I like to think of it as a completion of the usual free product. So I'll denote it by this, which is the usual free product, and I'll put a hat to indicate it's some sort of completed free product. And there's also versions of free products with amalgamation and H and N extensions. I don't want to write all that down. The upshot is one can mimic the conclusion of Stalling's theorem. And this is somewhat ad hoc, but I just found it convenient to have some kind of definition to state a theorem. So let's say a P prime group has infinitely many n's. You should write this. If actually I don't know an intrinsic definition, and that maybe is I should ask some group theorists about it. This is nice because you can say. But I'll simply take the conclusion from Stalling's theorem and say it holds in the pro-finite setting, which maybe it's still on the blackboard. Yeah, that thing here. So, in fact, if I'm really cheap about it, I can just put in the appropriate words and say the pro-finite free product or pro-finite version of H&N extension over a finite group. But let me say it properly. So and maybe since it's a lot of words to swallow, let's just concentrate on an example. So you could take this example, for example, and just take its pro-p prime completion. Group. And just for future, I should have said this, but it gets a bit tedious to have so many definitions. If G is discrete, let me write G hat. This is usually the pro-finite completion, but here I mean the pro-p prime completion, which is the inverse limit of all pro-p prime, sorry, all p prime quotients of this. Okay, so I haven't been very efficient with the blackboard, so let me, yeah, doesn't matter. So, let me state theorem 1. Actually, it would be nice if I didn't erase this. In fact, I don't want to erase anything, so you can warn me when I get to this side of the room not to erase these theorems, because I want to say something about the proof if I have time. I'll call this theorem 1. And theorem 1 is the analog, well, I did erase the thing with Bresler and Ramachandran, but it's an analog of that theorem. So, in fact, it's word for word the same, except the notions are different. So if G is pro p prime group, which fits into an extension, let me write it, and I don't know, H maybe. And this is extension in the sense of pro-finite groups, where this is topologically finitely generated. No. Sorry?
On the left it's starting on the 0.
Oh, yeah, sorry. 0 is 1.
Well, there's 0.
It makes a lot of,
Tradition.
yeah, I know. Yeah, no, it's, and this has infinitely many ends in that sense. And since I want to save the second blackboard for the theorem, second theorem, let me just squeeze in the conclusion here. Then G is not the fundamental group of a smooth projective righty, and I mean the pro-p prime part of that. So sorry about the compression, but I don't want to write in the next blackboard.
Are the definitions set up so that if you were over C instead of over a finite field, that theorem would apply this?
Yeah, so the definitions are set up so that if you start with a group with infinitely many ends in the usual sense,
Yeah.
and take its pro-finite completion, then it would be in this sense. It would be the pro version. Because, yeah, I should have said, maybe yeah, since you mentioned it, just to give an explanation, if I take, and this is true for other operations I don't want to write down, but it's in this book that I mentioned. If you take the usual, take G1 and G2 are discrete groups, and take its completion in this sense, then this is what you get. So these operations are compatible. So that's sort of an answer to your question. So if, yeah, 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 yeah. Yeah, it doesn't apply. So the theorem that I originally stated is actually a stronger theorem.
Yeah, then this one.
Yeah.
Yeah.
But it's sort of an analog.
But it's not even clear a priori without one.
Yeah.
way it's set up, that the theorem is actually stronger.
Yeah, no, that theorem is stronger, but this is just sort of, yeah, I mean, it's the best I can say at the moment. Right, yeah, so this is not supposed to be here. So then the theorem 2, which unfortunately I don't have as good a version of this. So my motivation was this theorem of the one-relator Kaehler groups. But, and this is the reason I needed to fix a prime. Actually, I'm not going to fix a prime. I'm going to, so let me write this down properly since I'm going to mess it up otherwise. I need to get the order of the quantifiers. Theorem 2. Okay. Yeah.
Theorem 1 is a theorem that G is a condition on an extension of the cannot be topologically.
Oh, sorry. So if I can take a G, which is an extension of a group with infinitely many ends by something which is topologically finally generated, then it's not coming from. No, it's not saying that because, yeah, because you have to have an H. Yeah. Yeah, sorry. If this H was not there, then there's no statement. That's right. That's right. I'm not trying to contradict that. Maybe I should just focus on the corollary. 'Cause, yeah, I admit this formulation is a lot of notation to absorb. But for example, this is Gromov theorem holds. So Gromov's theorem. Holds in this setting, i.e., if you start with a smooth projective righty, then this is not a free product, or not a coproduct, except if one of the factors is trivial. Yeah, so maybe the role of the K is just confusing the issue. Let's say there is no K, just to make it easier to swallow. Then all the condition is on the H.
I asked my question.
Yeah, sure, I understand.
Could a group which has infinitely many ends be topologically finitely generated?
Yes.
That's possible.
Yeah, yeah. So if you took the free group and completed it, it would. Yeah, yeah. Okay. So maybe, yeah, maybe I'm trying to say too general a version. So just focus on this if you're confused by the original statement. Okay. So maybe theorem 2, I'll go over here. And yeah, maybe all this notation is a little bit tedious, but it makes it easier to state things. So let me introduce a class. So let me just write script P of P is equal to the class of groups, pro P prime groups, which arise this way. Over K. And as I said, K, you can just, for the purposes of this talk, just fix this one. Yeah, P prime, sorry. Thank you. And then it just makes it a bit easier to say. So, for example, let me just quickly revise this statement, and this is not in there, and so on. And so the theorem 2 is supposed to be an analog of the one-relator story. It's not as good as I hoped for, but it's at least something. So if, yeah, so I was going to write those down from my notes, otherwise I'm going to screw it up. Yeah, so suppose I pick a G in this set, and suppose I know it's actually the P prime completion of one related group. That's a strong hypothesis, but okay. Then ideally I would like to say that it's of the form I wrote down earlier in the theorem of Biswas and Mohan and Kachik, but it's not quite what I have. Then for all, this is what I can say. All but finitely many primes. And you should assume these primes are different from P. So you may as well just add finite many primes. If you take the pro-L part, maximal pro-L part of this, then it's not of the form I said before. So this notation is the maximal pro-L. An L group is just an inverse limit of, sorry, a pro-L group is the inverse limit of L groups. G. This is of the form, you take a genus G surface group, which I'm going to denote by gamma G, and take its pro-L completion. So maybe I'll just say it in words. Okay, so this is sort of a weak form of this one-relator Kaehler group theory, but it's something. Okay. Sorry.
Was gamma the group you wrote down?
Yeah, yeah. So maybe to be explicit, gamma is. I just mean the classic version. Let me squeeze it here. So your classic, I can just draw this picture for you, right? Yeah, that one. I like drawing. Okay, I have colors here. There's no power. Okay. Yeah, that was your question. Yeah, it seems weird, but the point is that even if you apply this theorem to the characteristic zero case, the fact that you're throwing away some primes actually sort of absorbs that M. Yeah. So that M, if you pick the L to be co-prime to M, it sort of disappears. Yeah, you could take the. Yeah, that's right. Yeah, that's right. So the pro-nilpotent, how do you say it? Pro-finite, there's a lot of pros. Pro-finite, pro-nilpotent completion would be the product of all these GLs. Unfortunately, I'm missing some Ls. Sorry? Yeah, so, yeah, thank you. Where G is independent, so, yes, yeah, that's actually important. So G is just half the first Betti number, which begs the question, why is this even? But it is. So this is the half the first L-adic Betti number. Yeah, so it's uniform. Okay, so sorry that was a bit of a mess, but hopefully it's clear. Is it clear what the statement is? Okay. Now let me, I have about 20 minutes. And I realize you're hungry and I won't take too much time. Okay, so I'm not going to really give a proof, but sort of an idea of the proof, or indicate what are the methods. Okay. So let me state a theorem 3. Which is sort of the main workhorse in this subject. And I should point out that this was, in the Kaehler setting, this goes back to, maybe I should give the credit to Johnson and Rees. It's a very short paper, but it's a nice paper. Again, the late 80s. In Kaehler setting. Okay. So let me state theorem 3 in a slightly weak form, and then I'll just, without writing any notation, because it'll be messy, explain it. You can generalize it a little bit. So, I have this class. So if G is in there. There exists a map from second cohomology, and you may actually wonder what this means. I mean sort of continuous cohomology. And L is always just some prime different from P, such that if you take the cup product pairing, into H2, sorry, G, and then composed with this lambda, this is going to be non-degenerate symplectic. Sorry? QL. Thanks. Okay. So the version that I actually use is slightly stronger, but it's a bit messy to write, and it's going to get late, and so worth it. Let me just say there's a slightly stronger version, which I don't want to write explicitly. More general statement allows coefficients in a representation which is orthogonal with finite monodromy. Say the orthogonal group of OA and G module. These are all continuous modules with finite monodromy, meaning finite image. So maybe
It just comes from this lambda.
yes, this is hard life.
From the Kaehler
Yeah, yeah. So the proof, can I just say it? Proof is hard Lefschetz. So yeah, this is the only non-trivial part. The story, in characteristic P, it's of course a theorem of Deligne that you have hard Lefschetz in analytic cohomology, and that's the only. So without writing a big story here, proof use hard Lefschetz. Even for the souped up version, which I didn't state. Generalized version. So I didn't really want to write it down, but there's a slightly more general version. But you can, since it's finite monodromy, you just take a covering and then reduce it.
Sorry, how do you get from group chronology to chronology in space?
Yeah, right. Okay. So maybe I'll write it here. So I'm going to be a little bit, we can talk later if you like, but I'll just give you the idea without writing details. Okay. So if you're working over C, then there's a classifying map from B, the space maps to BG, and there's a map backwards, and this still works in this setting. But in this case, you can check it's actually an ISO. It's not an ISO here, but it doesn't matter. It's a map. And then on this end, you use hard Lefschetz to sort of take it up to the top degree cohomology. Say n is the, or let's say d is the dimension. Then you take the Lefschetz operator. I don't know. You need to go d minus 1 times. You can tell me if I need to change that. And that'll go to the top level, which is Q, by Poincare duality. So that's where that comes from. Okay. Right. So yeah. So maybe I'll say a word about this. So I don't want to. Yeah, I think I made a mistake to try and explain the general thing. Let's concentrate on this Gromovian version.
Would this possibly depend on which X you choose?
Yes, but the G, once you fix the G, this. Oh, I see. You're asking about this end.
Given a G, could there be different X?
There could certainly be different X's. Yeah. So this is just an existential statement. I'm just saying there is a lambda, which may depend on the X. Any other questions? Okay. So yeah. So let's just say how this works. And I'll be really sketchy about this. Since I don't think I have too much time, at least one indication of a proof is good. But if I can do the second theorem, that would be even better. So sort of not, maybe even sketch is an exaggeration of that corollary. So, so in discrete group theory, you have something called a Courage subgroup theorem, which tells you that you can always pull out a free factor of free product, and there's a version in this setting. So by the appropriate form of Courage subgroup, you can choose an H in here which is an open subgroup, so in particular finite index of this form. So it's going to look like a free group on 2 letters, at least 2 letters. And then something else which I don't really care about. M or L. Okay. So, and because this condition of being in, I should have said it, but I guess it's obvious, this condition of being in P, bracket P is stable under passing to open subgroups, you may as well take these to be equal. So, may,
Quantify state, you say you given G1 free product T2.
Given this, yes.
There exists another subgroup H,
Yeah.
which is of that form.
Yeah. So given you can find, yeah, sorry, there exists an H of this form. And now maybe I should write a separate line. You can assume, just to make life simpler, that these are actually equal. So in other words, that the original group is actually the group on the left. Okay. And now I'm just going to wave my hands, literally. And it depends on L. So everything's topologically finitely generated. I should have said that at the beginning. So this is. And that it depends on the rank of the abelianization of this. If the rank is even, if the rank is odd, that's the easier case, then the rank of this whole thing is going to be odd, but that will contradict this. So maybe I should have stated a corollary of this is the dimension of this space is even dimensional. So if you have a group with odd abelianization, it can't be in that class. So if L has odd rank, then you immediately, just using the corollary to that theorem, see that this is not in here. And if it's even, you actually have to do something a little more delicate. You actually use a character which is non-trivial on this factor, trivial on these factors, and that's why it needed this slightly stronger version that I didn't really state. And then play with that, and then you'll see again, in the second case, it again violates that theorem. So in either case, you can check that it violates theorem 3 or the corollary to theorem 3 so that it rules it out. Okay. So I have a few minutes, which is good because I wanted to say a word or two about theorem 2. Any questions?
So you can use that character trick even to rule out free products, free groups, like
Yeah.
all the time.
Yeah. This works over C. This works over C. Yeah. This is actually where I started playing with it over C, and then I realized you could actually do it in positive characteristic. Okay, so let me say a word about. Oh yeah, good question. I would like. Okay. Is everything true for normal varieties? I would like to think so, but I don't want to stick my neck out. But I'm sure that it should work. The only thing that maybe is a little tricky is this one. But I'm thinking that instead of usual hard Lefschetz, you would. Ah, okay. Yeah, I mean, there's some tricky. Yeah, normally I'm used to resolving singularities, so let me take that back. If you could resolve singularities, I'm pretty sure it's true. If you didn't, you would somehow have to cut it down to the surface case, and so I think it's probably okay, but maybe we can talk later. Okay, so let me say a word or two about theorem 2. And because I actually have some questions, maybe not questions that are interesting to anyone else but me, but the proof of this theorem is entirely cohomological. And in the usual version, there's a geometric part, which is missing. So again, to save time, let me just copy from my notes. It'll be very sketchy, I apologize, but I think there's no... Okay, so again, we're going to use theorem 3 as the main piece of, the main tool. But then there's some group theory one has to do. So what theorem 3 tells you that if you take the cup product, I'll just sort of rewrite it. G is now that guy. And I'm just going to write a few things. Sorry, this part I already said, so maybe there's no question about that. Now I'm going to take the maximal pro-L quotient. So this is, the statement is that this is non-degenerate. Sorry? Yeah, I did. I did say that. So let me take it back. Yeah, okay, right, I did say that. Yeah. Not, sorry. Okay, there you go. Okay, yeah, let me not repeat it, but this is non-degenerate. Okay, so then there are some things which I can't really justify, but I'm going to insert L. In other words, I'm going to pass from G to the maximal pro-L quotient. It's not actually difficult, but I don't want to explain. And then you want to pass from here to finite coefficients. This actually takes work. So this is actually where the major work is. And this is actually where the reason is I have to avoid certain primes. Okay, I didn't say anything about one-relator, but because it's one-relator, the standard computation, this actually counts the number of relations. So what am I saying? I'm saying that the work is that this is a non-degenerate pairing. And for L large. And also we can assume that, let's call it 1, that if you Booleanize, this is torsion free. Again, for L sufficiently large. And maybe I can give you an explanation. I don't use this, but you can think of this as the first L-adic homology of X, and then there's a theorem of Gaber, sort of, that says that if you pick L to be large enough, you should avoid any torsion. But actually, you can just do it more elementarily in this case. So once you have that, you can apply certain group theory. This actually shows you that this is a so-called Demoshkin group, if I'm pronouncing this correctly. So and then there's a classification of such groups, at least for L odd, but we're taking L to be large enough, so it doesn't matter. And the classification, maybe I'll just say this. Very quickly. So the classification is actually kind of cool because it basically says that if you write down what you get, then for some g, and the number of generators is necessarily even, you can uh, 2g minus 1, 2g. Okay, so it's of this form for some n and g. Now use condition 2, and you'd say, well, if this n was positive, you'd get torsion, and that's going to be ruled out by condition 2, so this actually doesn't appear. So use so this actually goes away, and now you've got your surface group. It's sort of magic, I mean, for me, because there's no geometry at this point. You sort of just classify these things, and this is what you get. And then maybe a little bit of argument shows you that this G is independent of the L, because the only G, sorry, the abelianization has to be the first homology, so the rank of that is has to be the first Betti number. So that's the idea. What bothers me is that over C, maybe I'll just mention this quickly and I'll stop. You get much more over characteristic 0 in general. For a one-relator group, you can actually look at the Albanese map. And under the conditions one-relator, you can actually show the image as a curve. And you argue with that, and you say that you actually show that the fundamental groups are almost equal. I mean, that's the way it grows. So it's actually a geometric idea. Here, there's no, I would like to think this is true, but I have no idea. Because at the back of this argument that the image is a curve is the Castelnuovo-Diffrantius theorem, which requires closeness of two forms, holomorphic, I mean regular two forms, which can fail on positive characteristic. So the question is, can you do this in general? Okay, so I should stop.